Sid is joining us over Zoom. If you want to take it away, Sid, go ahead.
It's a pleasure to introduce Rachel Holliday, and I'm so sorry that I'm not able to be there with you all. I'm at home. Rachel is a PhD student at MIT in EECS. She works with Tomas Lozano Perez and Leslie Cabling and with Alberto Rodriguez on robotic manipulation. I've known Rachel for quite a while now. She was an undergrad in the personal robotics lab at Carnegie Mellon, where she did her bachelor's degree in computer science and in robotics. We wrote a bunch of papers together, and then as much as I wanted her to come and do a PhD with me, she decided to run away and do it at MIT, and I'm sure she regrets that to this day. But hopefully we will get to work together at some point again. Rachel's written several papers, but I think what I really appreciated about her is her ability not just to prove theorems and write algorithms, but also to get things running on real robots. And so that's been something that's been a mainstay throughout her career. Rachel will be here for the rest of the day, and I'm sure she'll be available for meetings and questions and stuff. Take it away, Rachel.
Thanks, Sid. So, as I mentioned, my name is Rachel, and I'm going to be talking today about constraints in planning for forceful robotic manipulation. And as I mentioned, this is work done jointly with my two advisors, Tomas Lozano Perez and Alberto Rodriguez, and we're all hanging out at MIT. So generally speaking, I'm interested in planning for sequential contact-rich manipulation across a variety of domains and environments. And the bulk of my work in graduate school, and particularly the work that I'm going to talk about today, is focusing on a specific category of manipulation that we call forceful manipulation. So we categorize forceful manipulation as tasks where exerting substantial forces is necessary to complete the task. And by definition, any task that involves contact, therefore involves force. But we focus on tasks where generating and transmitting forces is a limiting factor that has to be reasoned over and planned for. Additionally, another characterization of the tasks that we're interested in is that they involve multiple steps. I'm not just interested in what the isolated action of twisting a nut on a bolt, but kind of all of the reasoning that leads up to that. Can I do that twisting with my hand, or do I need to go grab a tool? And if I need to go grab a tool, how do I grasp it? How do I do the motion to get there? And how can I do this in a variety of environments and hopefully do so in a way that's robust to uncertainty? And actually, those two things are what motivate us to take a more model-based planning approach. One is that we're interested in longer sequences of tasks, which learning-based methods can sometimes struggle with. And two, we're interested in what my advisors call aggressive generalization, and that we want to be able to adapt to a variety of different objects and environments. By definition then, because we're taking a model-based approach, we are going to assume throughout the talk that we have access to models of certain things. I will say there are lab mates in my various labs that are looking at how can we learn these models or acquire them for perception, and this is a point I'm going to touch in back on at the very, very end of the talk. So given that motivation, let's break down what we're going to be talking about today. So we're going to start by assuming that we have our forceful manipulation tasks as a fixed sequence of actions, and that our goal is going to be how do we find the parameters of those actions. And so this is going to allow us to frame the problem as solving a constraint satisfaction problem, where the parameters that we want to solve for are the decision variables within the constraint satisfaction problem. We're going to talk through what are the constraints that kind of shape the solution space, and perhaps unsurprisingly, given all the titles, we're going to focus in on formalizing those force-related constraints by conceptualizing something that we call the forceful kinematic chain. And this will, get us pretty far. We're going to show it on a sequence of tool use tasks. Here, our illustrative example throughout this half of the talk is going to be if we want a robot to pull up a nail using the claw of a hammer, so a very kind of forceful interaction task. But this won't get us all of the way, as you may guess, because it's only the first half of the talk. That initial assumption of assuming we have a fixed sequence of steps is pretty limiting if we want to get to that generalization goal. And so in the second half of the talk, we're going to focus on how formalizing those steps as more general operators is going to allow the robot to plan its own sequence of actions, and essentially it's going to be evaluating its own constraint graphs, which is going to allow the robot to plan more generally. And for this, it's going to allow us to, in this case, the example task is opening a push-twist childproof medicine bottle, and how could we accomplish that same task in a variety of environments, and the robot searching over a whole bunch of different strategies for accomplishing that same task. We'll come back to appreciating what's truly going on in this video. And I want to mention, just kind of as a preview, in the first half of the talk, we're going to be borrowing heavily from mechanics. And in the second half of the talk, we're going to be leaning into what's called task and motion planning. Throughout the way, we'll also do a bit of dives into robot motion planning as well as manipulator control. So those are some of the topics that are coming forward. Before we jump in, I do want to situate our work with respect to what's been done before, just a very small sampling. The Matt Dougher's group considered a specific instance of forceful manipulation where the robot is fixturing an object against a human that is exerting forces on it. We'll see in the second half of our talk that our robot is going to be both the agent that is exerting forces and the agent that is fixturing against the forces, so there's no humans. We saw a video of using a childproof bottle as an example task. This is also something that was looked at by Peter Allen's group a while back. Although their bottle has skull and crossbones, so is it medicine? I don't know, I don't want to ask. They formalized this task as kind of treating it as a finite state machine, and so again, it has this kind of fixed sequence of steps, and again, we want to get to a point where we allow the robot more generality. And lastly, the last one I want to mention is that planning with multi-step tasks considering forces, the most related work is out of Marc Toussaint's group. They also take a task and motion planning approach. They use an optimization-based method. We use a more sample-based method. There are different trade-offs in terms of how we formulate the problem. They can handle dynamic motion, so here they show throwing, and at the moment we don't deal with any dynamics. They do formulate in only considering linear forces and therefore cannot reason over torques, which we consider pretty critical for a lot of tasks. So just different trade-offs there. Speaking of torques, before we go any farther, a slight timeout. Wrenches versus wrenches. So there is wrench the tool, and to kind of clear up any possible confusion, I'm going to call this a spanner throughout the talk to differentiate it from a 6D vector of forces and torques. And I will slightly abuse notation in that sometimes when I say forces, I mean forces and torques. I use forces somewhat interchangeably with wrenches. Wrenchful manipulation sounds even more confusing. So this is wrenches versus wrenches. Everyone good so far? Cool. OK, so let's dive in specifically into how do we formulate these constraints. So let's define this illustrative task that we've talked about before, where we want a robot to use the claw of a hammer to pull a nail out from a block of wood. And as I mentioned, for now, and we'll relax this later, I promise, we're going to assume that we have a fixed sequence of steps that we want the robot, in the way we want the robot to accomplish the task. So we're going to say, OK, the robot, the way you're doing this is maybe first you grasp the tool, then you're going to bring it in contact with the environment, in this case bringing the claw in contact with the head of the nail. Then you're going to actuate, do that arcing motion to pull it up. This is kind of critically the part where the forces come in. And then once you've completed the task, do please put the hammer back where you found it. And it's useful to break up tool use into these types of stages because it allows us to identify for what are the pieces that the robot needs to solve for. So we've highlighted these in different colors. In green, the robot needs to pick how am I going to grasp the tool. In blue, how am I going to situate the tool with respect to the environment. And then highlighted in red are all of the different motion paths that the robot needs to plan, some of which involve forces, some of which don't. And all of these are essentially, as I alluded to before, are high-dimensional continuous decision variables. And all of these critically have constraints on them. Again, some force-related, some motion-related. And they all have dependencies between them. As a very simple example, you can imagine the path to get to the grasp has a dependency on what that choice of grasp is. So this setup gives a constraint satisfaction problem where we need to find the decision variables, whether the path, poses, and configurations, such that you satisfy all of these constraints. And to really dig into this, I'm actually going to visualize the constraint graph as a network where the nodes of our graph are going to be the different decision variables that we need to solve for. So again, in red is the paths, green is the grasp, and in T is the tool pose. And throughout this next bit of the talk, we're going to map out kind of populating this graph in terms of what are the constraints on these different variables and what are the dependencies. So the first constraint that I want to talk about, again, perhaps unsurprising, is the force-related one. So forces come into play right when we're dealing with that actuation step of actually pulling out the nail. And so if we zoom into looking at that, when the robot is acting, we can think of the overall system, in this case the robot and the grasp tool. as a kinematic chain, and that this kinematic chain is made up of some series of joints. And some of these are directly robot joints, and some of them are frictional joints made based off contact, in this case, our grasp on the tool. And for now, we're going to assume that the environment that you are acting on is rigidly bolted. In this case, there's an 80-20 rig. We are going to relax this assumption later, where the robot is going to be responsible for doing that fixturing. But for now, it's fixed. So given this, the constraint that we need to evaluate, the thing that needs to be true in order to accomplish our task, is that when our robot is exerting the wrench, in this case as it pulls up on that nail, we want to ensure that the forceful kinematic chain formed by these joints is maintained. That is to say, in the face of the exerted wrench, each of the joints can resist the wrench that's being imparted on it without breaking or failing, and we'll define what that means. Another way to think about this is that our constraint is that we want our robot to be strong enough to complete the task, because there are forces involved. So the way we're going to attack this is that for each of our different types of joints, we're going to model what is the space of wrenches that this joint can resist. And if the wrench lies within the set that we can resist for all of our joints, we're going to say that the forceful kinematic chain constraint is satisfied because our chain is stable. I wildly overuse stable. Control theorists aren't happy. It's OK. We'll get past it. So let's look at how we mathematically quantify for each joint how much wrench that joint can handle. So let's start off with our robot joint. What would it mean for a particular robot joint to be strong enough to complete our task? So robots have torque limits. They're limited in amount of torque they can resist before they torque fault. If you've ever seen a robot do this, it makes a very sad noise. So breaking this robot joint, it doesn't correspond to breaking the robot in half, but rather the robot experiencing a torque fault and failing. So to test if the robot is strong enough, especially this particular robot joint, what we need to do is we need to transform the wrench experienced during the task into torque experienced at the joint. And so the way we're going to do that is we're going to first transform the wrench experienced at the task into the wrench experienced at the end effector. And in order to transform wrenches at the end effector to torques of the joint, we're going to use an operator called the manipulator Jacobian. For anyone who's unfamiliar with it, so this is JM. If you take the forward kinematics of a robot and differentiate it with respect to time, you get the Jacobian. The Jacobian maps end effector velocities to joint velocities. And beautifully, I think, is that if you take the transpose of the Jacobian, it maps wrenches at the end effector to torques at the joint, which is exactly what we want to do. I do want to highlight that the Jacobian is configuration dependent, is dependent on your joint angles Q, which if you think of your own arm as somewhat intuitive in that in different configurations you might be able to resist more or less force, particularly if you're at a singularity. And so our configuration dependent Jacobian captures that. Excuse me. And so we're going to take our wrench, transform it into our Jacobian to get our torque at the joint, and then to see if we are strong enough, we simply compare it against the robot's torque limits, and if it's inside, we're good to go. Our joint is strong enough, and we can do that for all of our robot joints. I am particularly fond of redundant manipulators, so we're always going to have 7 jointed robots, and we can do this for all of the joints. Cool so far? OK. So this is for our robot joints. We also want to consider frictional joints. Now in this case, we only have one frictional joint, which is the grasp on the tool. We'll get into kind of a more general set of more frictional joints. So the question becomes what is the space of wrenches that can be resisted by this frictional joint? And to answer that, we need to dive into what is the type of contact that's being made here. And so if we zoom in to what is the hand, within our work, I mainly use parallel jaw grippers. And so for this frictional joint to break, I'm going to say that would mean that the object would slip in the hand. So we want to prevent in-hand motion. So given a grasp with a parallel jaw gripper, how can our object move? I'm going to argue in 3 dimensions the robot cannot move kinematically due to non-penetration limits. If you think about in 3 directions, for the object to move sideways, it would have to move through the finger. And I'm going to assume that our fingers are rigid and they do not allow motion within them. And so we assume that you can resist basically infinite force and torque in each of these 3 dimensions. This constraint holds most of the time. We did accidentally break a 3D printed finger in half, but it's a robot finger, not a human finger, so it's all fine. So that's in 3 dimensions. What about the other 3 dimensions? In these 3 dimensions, it actually is feasible for the object to move. And so the only thing that is preventing that motion is frictional forces. Which then raises the question, do we have enough friction to resist the external wrench? How much frictional support is our contact providing? And the amount of frictional support that our contact provides, because we're dealing with this planar grasp, right, we're only dealing with 3 dimensions, is quantified by this representation called the limit surface. And we use 2 constructions of the limit surface based off the type of contact that you're making. One is the ellipsoidal approximation, and one is the generalized friction cone. And we're actually now going to do a bit of a mechanics deep dive. For anyone who's not familiar with the limit surface, we're going to overview a little bit more what is it, and then how you actually use the ellipsoidal approximation construction. If you're interested in the generalized friction cone details, that's in our paper, where I'm happy to talk about it more. OK, so let's dive into mechanics. So the limit surface defines the set of all possible frictional wrenches that our contact can provide. And so the way you can think about it is, if our external wrench lies within the boundary of this set of wrenches, then our contact is stable, and there's going to appear no motion. Basically, our friction overpowers that external wrench. If our wrench lies outside the boundary of that set of wrenches that we can resist, the object is going to slip. It's going to move in the hand because friction has lost out. The way the object slips, particularly if you're using the ellipsoidal approximation, is actually very well characterized. We've used it in the context of doing in-hand manipulation with motion cones, but we're not kind of leveraging that within this work. We're only checking, do you slip or do you not? Any kind of slippage is not OK. And so if you have circular patch contact with uniform pressure distribution, which is true most of the time in our grasping, then you can use what's an efficient and kind of compact representation of the limit surface, which is called the ellipsoidal construction, which I've drawn here, somewhat cheating the axes. And so this is an ellipse that's in 3D, right, because we're only considering planar grasps. And the shape of this ellipse is determined by this matrix A. The matrix A is very well defined. It's a function of our grasping force, n, which we control, our friction coefficient, mu, which we have an estimate of, our radius of contact, which we know because we know the shape of the objects, and an integration constant, c. And so this is kind of the characterization of the limit surface. This is a little bit of math. How is it actually used? Let's walk through an example. So let's say we have our wrench experienced during the task. We're going to assume that we have an estimate of this. In practice, we kind of empirically experimented until we got a decent estimate. And using our grasp relation, we can transform this wrench experience at, in this case, the tip of the tool, into our contact frame. In 3 dimensions, right, we assume we can resist infinite. In the other 3 dimensions, we're going to take a 3-dimensional slice. And we can actually plot that wrench within the context of our ellipse. And for the sake of this illustrative example, the wrench exceeds the boundary. And this is very easy to evaluate based off the definition of ellipse. Fastest math in my code. And so we can evaluate that this is a bad grasp because it would lead to the object slipping in the hand. It would break the joint. It is not a stable forceful kinematic chain. So in this case, you would hope that the robot, or you want the robot to, say, pick a different grasp. And because it's a different grasp, when you transform it and take a 3-dimensional slice, it is a different wrench. And for the sake of the example, you might imagine that now it's a different wrench which lies within the boundary of what our friction can resist, and therefore is a valid and stable grasp. So bringing this and kind of summarizing it all together to evaluate for our frictional joints, which here we've talked about a grasp. We'll consider other frictional joints. You can evaluate whether a grasp is stable, or whether, frictional contact is stable with a combination of kinematics and friction. And if we zoom all the way out, we can now evaluate all of the different joints within our forceful kinematic chain. And for a given set of parameters, if everything is stable, then our constraint is satisfied. Cool? OK. So where does this come back? Taking one step further, back into our constraint graph. How does this fit in from a constraint perspective? It actually comes in 2 different places. One is that we want our grasp to be stable. And the other is that while that motion, that arcing motion of tracing out a particular path to pull out the nail, every configuration along that path needs to be stable. So this captures our force constraints. We do have a couple of motion constraints that I'll go over pretty quickly. As I just mentioned, for this path, we want to trace out some motion. You can imagine for the hammering task, it's this arcing motion. And so how do we actually capture that? What we're going to say is, as a function of this tool starting pose, we want to trace out some path for the tool. I've drawn a general path. You can imagine, again, for the hammering task, it's this arcing motion. And these are waypoints. These are position and orientations. They're waypoints in SE3. And through the grasping relation, think about relating the path of the tool to the path of the end effector. And that end effector is attached to a robot arm. And so your problem now becomes, how do I find a path, a series of joint angles for my robot, such that it traces out an end effector path, which in turn traces out a path for my grasped object. And so I'm going to call, this is our follows constraint, which also adds a reachability constraint on our grasp and on our tool. And the only last thing to cover up is that we want our manipulator motion to be collision-free for most of this. OK, so this gives us all of the constraints, but we're not quite done yet because we have to map out the dependencies between all of these. And as we do that, I'm going to very briefly mention kind of how we solve for each of these. So we sample from continuous sets, what a possible grasp and possible tool poses. We then feed that in to computing our follows path. To find a path that hits that follows constraint, we actually leverage a specialized graph-based planner that uses the Frechet distance to capture this notion of following. This is actually work done with SID when I was at CMU, along with the lovely Oren Salzman. So we just kind of leverage that directly, adding in the stability checks. Once we have those paths, you kind of have all of the dependencies in order to plan the rest of the paths, which are all just, can I find collision-free motions? It's not terribly important, but within the context of this, we use a bidirectional RRT. But you can use anything that finds collision-free paths. Cool. So now we've got kind of our entire constraint graph, which maps out our entire task. And leveraging this, I will say that we take a very simple way to solving the constraint satisfaction problem, which is we work through, and if ever we can't find a solution, we restart. It's kind of a rejection sampling method. It's the simplest way you can deal with constraint satisfaction. But despite it being so simple, we can apply it to a variety of tasks, some of which we've hinted at. And so there's our favorite illustrative example we've been using throughout, which is pulling a nail out with a claw of a hammer. As you might have guessed, during our mechanics deep dive, we use a screwdriver to drive a screw. There's also cutting, although I'm going to call this notching, and we're going to get back to cutting later on in the talk. Notching a block of wood with a plastic knife, and then also tightening a bolt with a spanner. It's the only tool I'm comfortable taking on a plane. I'm worried about the hammer. Cool. So I do want to just hammer in for a minute, if you pardon the pun, that you really do have to care about these constraints by thinking about what happens if you don't care about them and you violate. So let's say I comment out the constraints of the forceful kinematic chain check, and I try to accomplish this task. I'm going to color the robot arm from green to red in terms of how close you are to your torque limits. And if you don't care about the constraint, the robot gets close to its torque limits. And if you try to accomplish it on the robot, you're going to directly hit that torque fault because you did not satisfy that constraint. And so if you comment back in that constraint, the robot makes a series of different choices. Again, remembering that our torque check is configuration dependent, so it's going to pick a different configuration for the arm. And now if you repeat again, we satisfy the constraint, and the robot is able to successfully complete the task. So just these constraints do matter and do affect task success.
Can I ask a quick question?
Yeah.
I have a stupid question about why you grip it using that particular grasp, and in that it's the motion, the direction of levering is the direction that you can slip it, right? Why not grasp it?
Yeah.
The other.
So this question has come up before, it is not dumb. So we only check for if the grasp is feasible. You could think of an alternate way to frame this is that checking more for an optimal grasp in the sense that one that minimizes any chance of slippage. So in this case, this grasp is feasible is not particularly the best one, I would argue. But it is the same from my advisors that the problems are hard enough, we only want our robots to be good enough. But yes, this is your intuition is correct that this is not the best grasp. Cool. Oh, and just to clarify, in case this comes up later, all of the simulations are purely running visualizations. There's no physics being run there. It's only kind of our models, not anything else on top of it. Great. So this constraint graph really captured our entire problem, the entire problem in one slide. And this is because we had a fixed sequence of actions, and from there we kind of walked through hand defining what are our constraints and what are our dependencies. We built it up, and it solved tasks, and that was great. But this is fundamentally limited because our robot has no flexibility. It can choose different graphs and different paths, but it can't change how it accomplishes the task. And so if you have a different environment or different settings or things are not reachable, the robot can't kind of adapt to that. And that's what we want to focus on changing. So to better facilitate multi-step and kind of generality, I want my robot to be able to plan its own sequence of tasks. I'm tired of telling it exactly what to do and how to do it. And so to do that, we're going to need the robot to be able to generate its own constraint graph instead of us hand defining it and being able to evaluate on its own. And this is going to take us into the second part of the talk. Before we get to the bottle example, I want to stay for just a minute longer on our hammering task because we understand it so well, and think about how would we take that task and modify it in order to be able to plan sequences. We'll come back to the bottle, I promise. So at the very beginning, I defined these fixed set of stages, and stages was a very informal term that nobody called me out on. But now I want to formalize them into what's called various operators. And for now, these are going to be somewhat toy operators. What is an operator? An operator fundamentally is just a parameterized controller. We have some controller that we're running on the robot and is parameterized by certain values. We characterize this operator by the preconditions, which is what are the things that need to be true about the world in order to run that controller, and then the effects, what are the changes in the world having run this controller. And so if we take that first stage, we can imagine making, again, a somewhat toy operator that is moved to grasp, that the controller that's running is some position-based controller and a grasp controller, so it's parameterized by what is the path that I'm doing and what is that grasp. And its preconditions are maybe that I want everything to be collision-free. I start at the beginning of the path, I end at the end of the path, and then I end up also being at the grasp. So the reason why this is powerful, and the reason why this is worth doing, is that from this directly gives us a piece of our constraint graph. So you can imagine the parameters of our operators define our decision variables, and the preconditions, and to some extent the effects, define what are the constraints, and also with the preconditions effects, define what are the dependencies and what are valid operations to do one after the other. And so this is awesome and useful because if I have a sequence of actions, a sequence of operators that I want to do, this is often sometimes called a plan skeleton, then this automatically generates our constraint graph. It basically has all of the information embedded in the representation. And so if we define all of the operators, we no longer have to generate that constraint graph on our own. The robot can now evaluate its own constraint graph, and you can search over different possible constraint graphs in order to find a satisfying solution. And this is the kind of key step that's going to enable us to do planning over different plan skeletons, which is going to allow us generalization. Now that we've looked at this hammering, to really see it in action, I want to move back to a task where we have a lot of different solutions. Once we've defined really fully this task and understood it, we're going to come back to this idea of how do we plan. So as mentioned before, we're going to consider opening a child-proof push-twist bottle. And so in order to open it, it's a medicine bottle. We have to open it by both pushing down on the cap and exerting a twist. And we're going to say, sorry, I dropped my, is that while you're doing that, you also have to secure the bottle in some way. Before, we assumed that everything was fixed in the world. That's pretty limiting. Now it is the robot's responsibility for doing that fixturing. And then what's really lovely about this example is that there are so many different ways that you could accomplish this task. You can imagine maybe that the robot grasps the lid and exerts the push twist, and maybe it uses the frictional support between the table and the bottle in order to fixture it. Maybe if your table doesn't have enough support, as this table doesn't seem to have, then maybe instead the robot can do a pick and place operation to relocate the bottle into a vise and then use its fingertips to exert that push twist. Or maybe it relocates it to a higher friction area. In this case, we have a high friction rubber mat, and then it grasps and uses a tool in order to exert that same push twist. And you imagine that each of these different strategies are valid in different environments, right? This one is only good if you have a particularly high friction-y table, to be honest. And as an example, this one requires that you have a tool in the scene. And each of these, you can imagine, generate their own complex constraint graphs with the same kind of constraints we saw before. Things have to be collision-free and reachable. If you're exerting a force or fixturing against a force, that forceful kinematic chain has to be stable. And returning from point further is I want my robot to be able to find any of these solutions subject to those constraints and subject to what the environment allows. And so what we established earlier when we were talking about our hammering task is to do this, we need to define a set of operators. You can think of this as like, what is our robot action space? And then it's going to be able to sequence those set of actions in order to replicate the behavior that you see here. OK, so what are our operators? And I'm going to look at this again in the context of this specific example, but when we get to other domains, you're going to see that there's a lot of overlap in terms of what you can reuse. So before, we had kind of a toy example where we had move to grasp. In practice, most of us, to be more general, kind of separate that out, a move and pick, along with defining a move holding, which does a little bit more collision checking, and a place. And these are, I would say, fairly generic. And if you have these set of operators, you can do the normal sequence of pick and place actions and move objects around in the scene. But you can't yet exert that kind of push twist. And so we're going to have to define a few domain-specific operators. And so within this work, we actually define 3 different ways that you can exert the push twist, some of which I've kind of alluded to before, that you could grasp the bottle and exert the push twist, or you can make contact either with your finger, your palm, realistically kind of any surface that you want, any contact surface, or via a grasp tool. And so there are 4 different ways, but the underlying implementation between all of them has a tremendous amount of overlap. And so each of these are operators, and it's a valid question to ask, if this is running a parameterized controller, what is the parameterized controller that's being run for each of these operations? And to answer this, we're going to now do a little bit of a dive into looking at manipulator control. So let's say that you have a very simple robot. Why it's a simple robot will become clear in a minute. And if it's in free space, it's not in contact with anything, it can move in any direction, right? But it cannot exert force in any of the directions because it's not in contact. And on the opposite side, if we have a robot that's encased entirely in concrete, this is why I use a simple robot, nobody was harmed in the making of this figure, now it can't exert motion in any direction, poor robot, but it can exert force in every direction, right? Because every direction is in contact. And across this spectrum, position control is normally used here, and that's great for commanding motion, but cannot deal with any kind of contact or force. And force control, force control is useful in cases aside from when your robot is encased in a block of concrete. I don't want to give force control in the sick, but it does get very dangerous. But you might argue that what we're doing is we want to some extent to control forces and motions. And one way you could get around this, that you could do this, is there's something called hybrid position force control, which partitions the space and considers it in different directions. Sorry, Matt, we're going to do something a little bit simpler, which is going to use a form of compliant control called Cartesian impedance control. So for anyone who's unfamiliar, rather than directly controlling a position or controlling a force, impedance control is going to modulate the relationship between those two. And we often think of this as that the robot is rendering the behavior of a mass spring damper. Think of a mass spring damper as regulating the position between the relationship between motion and force. And because we're using Cartesian impedance control, the way that this controller is parameterized is that we have some set point that we're controlling to. Because it's Cartesian, it's going to be a set point in SE3. We have some stiffness matrix. In general, this is a 6x6 matrix. We're actually only going to consider the diagonal. What is the stiffness in each direction? And there's also a damping matrix. Again, in general, this is a generalized damping matrix. We're going to actually normally set it to be critically damped as a function of the stiffness. So this is stiffness. This is impedance control. How can we use it to kind of exert our push twist? How does that come together? So let's say we have our cartoon robot from before, now running an impedance controller. If the robot is in contact with an environment, let's say the robot is in contact with the ground, if you set the set point to be lower than the ground, it's going to try to achieve that and compress the spring. Compressing the spring is going to be exerting a force. Now you may rightly say, okay, the robot is rendering the behavior of a mass spring damper, but is it actually? And somewhat in a way that shocked my advisors and I, for the Franka Amica Panda, which is the robot that we're using, and for the controllers that we are running, it really does render a mass spring damper. For a given stiffness, the relationship between what is your offset and what is the force you are rendering is basically linear. You get Hooke's law out, which is what allows us to kind of really leverage that relationship and exert force through Cartesian impedance control. So thank you to the Franka. So given this is how we use Cartesian impedance control to exert force. And then to exert that twist, we're just going to set the series of set points to exert that twisting motion, offset by whatever we need to exert the desired force. And so just to kind of summarize, we have a parameterized controller where the parameters that the planner needs to select are what are the set points accounting for that offset, and what is the diagonal stiffness matrix that I need to specify. This is what our robot needs to decide. Okay, so this is the parameterized controller. It's used for all of our operators. There's a lot of overlap. Given that our operators are exerting force, we need to check that for all of our joints that the forceful kinematic chains are stable. And this is reusing kind of all the same mechanics tools that we had before. You can see that in these, all of these are basically forming different sets of chains with different types of joints. The way this comes up is that in our operator specification, a precondition of exerting any of these is that your forceful kinematic chain is stable. So that's how the constraint works its way into the specification. Another precondition, this is going back to thinking about the way we specified our domain, is that the bottle has to be fixtured or secured in place. And so we define 3 different ways that the bottle can be fixtured. You can have a second robot, should there be a second robot in the scene, forcefully grasping the object. Again, this is creating another forceful kinematic chain. You can have a vice in the scene, as we've kind of alluded to before. Again, the forceful kinematic chain here is the grasp. I call it a vice. It is a robot hand mounted to the table, because that gives you an electronic vice. Or you can use the frictional contact between the bottle and the surface, and here we either have the surface being the table or a high friction mat. And so bringing all this back, if we look back, returning to our operator list, we add operators for each of our push twist operators and then ones to actuate our little robot vice. You actually don't have to add any more operators. This is all specified in PDDL, and there are a couple other details about how we do derive predicates that I won't necessarily get into. It is now our robot's job to find what is this sequence of actions. And if we recall back, that sequence of operators defines our constraint graph. And so then it has to, in addition to finding the sequence of actions, what are parameters that satisfy those constraints? And so how do we both plan for those sequence of actions and parameters of those actions that satisfy the constraints? Okay, we skipped past the sound. Cool. So to do this, we're going to use something that's called task and motion planning, also called TAMP. And we're going to specifically use a framework created by one of my lab mates called Padiddlestream that I'm going to briefly summarize. So briefly, Padiddlestream uses what's called a series of streams. They're called streams. You can think of them as samplers. And these samplers generate possible instantiations of our decision variables just because they're continuous. You can think of sampling values. So an example of a stream is one that generates sample graphs from a continuously defined set. Another example of a sampler is one that generates motion planning paths. So we have these set of streams, and we're going to generate possible values, and we're going to hand these possible set of values along with that operator list that we built up, our start state, and some specification of our goal. And we're going to hand that to, in this case, a PDDL planner. And it's a discrete domain-independent task planner. We specifically use fast downward. And it is going to search over possible sequences of actions and then see, given the samples that I have, can I find satisfying solutions to those sequence of actions? And it is basically going to keep doing this loop. The paper has details about how it does it intelligently, of sampling and searching until it finds a satisfying plan. And the way I like to think of this is that this is very similar to a probabilistic roadmap, a PRM, if people are familiar with that. A PRM samples configurations, samples continuous configurations, uses that to build a graph, and then you can apply basically any graph search in order to find a path. In a similar way, Padiddlestream is sampling continuous values in order to build a PDDL problem, which you can then apply a domain-independent PDDL searcher over. There's a couple of details in that generating satisfying values is a little more complex than your normal PRM, but you can still think of it in this context of I am sampling values, searching over them, and kind of repeating until I succeed. So this is the planner that we're going to use, and now we can kind of appreciate the video that we had from before. Okay, plays without sound, cool. And so the robot is operating in a variety of different environments. You know, there are different bottles with different wrenches, different objects, different initial starting configurations. And the robot is finding a bunch of different possible sequences for accomplishing this task, you know, sometimes using the vice, sometimes relocating. Okay, let me do a pick and place in order to move to a higher friction area because the area I was at didn't give me enough support. In this case, it used the palm of its hand because that was a larger surface area, or different tools. And this is actually only a sampling of the amount of different plans the robot can find. Here's again, only another small sampling of the robot can kind of find any valid sequence of the operators that we're given, and so it's a very large combinatorial space, which is what powerfully gives us the generalization to interact in a lot of environments. Kind of as long as we can find a sequence of operators, we can adapt to kind of a lot of different settings and surroundings. Cool. Okay. So we've been focusing on this domain. I want to mention two other domains that we've been looking at. One is returning to if you wanted to twist a nut on a bolt. Here you want to exert torque about z, again, while fixturing. And what the robot needs to search over is that it can either twist using its hand or pick up and use a spanner, and it can fixture that bolt either by using a second robot in the scene to grasp it, or picking up a large weight, in this case shown in green, to weigh down the bar enough in order to fixture it. And this is where the generalized friction cone for checking forceful kinematic chain actually comes in. So it allows for much more general frictional joints. And again, I just want to show this is all of the kind of same things and a lot of reuse, the same controllers, a lot of the same samplers, and then you can use it to find a lot of different solutions for solving this problem. Cool. Go, robot, go. The last thing I want to mention, and I want to preface that this is work that is in progress, but it is too fun for me not to share, and that is getting a robot to cut vegetables, in this case a cucumber. And so we borrowed some assumptions, some great work out of Iowa State, Yabin Jia's group, where we both focus on domains where we can approximate the object as rigid, so you don't have to deal with kind of the fracture mechanics, and also that we're going to represent cutting as both first a downward press and then a horizontal slice. So now we have two wrenches to check against. And we're always going to insist that our robot does this with a knife. Right now we're not searching over different knives, but there are different ways that the robot can fixture the cucumber. A lot of this is going to look familiar in that we could have a second robot grasp it. We could make a frictional contact and press down with either our fingertips, our palm, or grasp tool. So there's still a general space to search over. We don't yet have the bimanual robot set up in the lab, so what I'm just going to show, again, it misses out on the generalization, which is a bummer, is I'm just going to show the robot focusing on doing the cutting motion. So here, the robot is reasoning over picking up, cutting. We used to use a plastic knife. Now we're using a real knife. It doesn't freak anyone out. It's all good. And here it's going to do that slutting and kicing motion in order to cut the cucumber. And we've also done this. We've done this a number of times. Again, this is still in progress. And also reasoning about how can it cut a banana. I personally prefer the banana because then I eat the slices after, and it's a good snack. I will emphasize that this is still in progress, somewhat of a function of the fact that we're using a Cartesian impedance controller within this robot. There's a limit to the amount of force we can exert. In some ways, this is nice from a safety perspective. In another sense, it limits how rigid the objects we interact with that we can cut. And so this object is more rigid than a banana, and basically the impedance controller gets stuck and does not exert all the way through, which we'll see just kind of bounces on it. As for cutting to go wrong, I think this is the safest way it could go wrong. So this is kind of a limit of using an impedance controller, and we might imagine that instead of using that as our parameterized controller, either going back to exploring force control or using hybrid position force control could allow you, at least for the way we have the robot set up, to explore stiffer material. I also want to point out, and if you've been eagle-eyed about the types of grasps, if you only pick a grasp trying to be resistant to the linear forces, you're missing the fact that when you interact and cut through the object is going to exert forces back on you. And so if you do not model that, you can pick a particularly bad grasp that when you go to interact with the object, and we'll see this happen here, is going to slip in the robot's hand. Now, if you model, even adding just a little bit of modeling for torque about y, then this grasp becomes invalid, and you switch over to picking grasps like this, where you can use the kinematics to bolster against that force. So we're still exploring this. There are still things to work out. That being said, even with these things to work out, this is a very simple model of cutting, and I'll be the first to say it. If you think about cutting in the kitchen, slicing, dicing, chopping, dealing with squishy objects, using the knife in a variety of ways, and my roommate gets tired of me filming her using knives, that there's so many things that you could do with cutting that we want to explore, and I see this as really just taking a first stab. So we've seen this framework applied to a variety of tasks, and I want to emphasize that equally important to this is that we want to be able to accomplish the tasks in a variety of environments in a way that's robust to uncertainty. We're dealing with real robots, you cannot get away from uncertainty. And so to look at that, I want to return back to our child-proof bottle example and think about, we mentioned one possible way to fixture was using the frictional contact between the table and the bottle. But if you don't have enough frictional support, you do not have a, I think this is the same table you all have in your Franca setups, that it does not normally provide enough support and would slip. We talked about how the robot in this case would then plan for using a different fixturing method, maybe relocating it to a high friction mat or a vise or whatever. But let's say something nefarious happened, someone slipped into our lab in the middle of the night and they swapped out our table. And all they did is a 400-pound table, but we'll skip past that. And they swapped out our table such that it has slightly more friction, such that the frictional forceful kinematic chain constraint is just barely met. It is right on the edge. Do you want to trust this? I would argue probably not. This is particularly brittle. You're really relying on friction to come through for you. And so to capture this kind of brittleness and robustness, what we do is we sample perturbations of our physical parameters, like our friction coefficient, our area of contact, the wrenches that we're exerting, and we basically, across a bunch of our samples, count how many of those lead to successes in order to form a probability of the success of the stability of our action. We can then take this and formulate the cost of an action as being the negative log of this probability of success, and therefore minimizing cost is going to lead to maximizing our plan success likelihood. And within our task and motion planner, Piddle Stream, it's fairly easy to incorporate costs if they are additive and functions of your parameters of your actions, which ours are. And so what this allows the robot to do is the robot can reason over the fact that fixturing with a vise is maybe more reliable than fixturing using friction because you're relying more on kinematics than friction, and so it can make these different strategy level decisions. Additionally, it can decide kind of on the more continuous level that between these two grasps, one grasp is more robust than the other, essentially because you are less likely to be plagued by uncertainty in exactly where you're grasping that object. So in this way, our robot can kind of reason over what are more robust things in order to deal with uncertainty in those physical parameters. And kind of wrapping this up, to summarize, we used a task and motion planner to generate a combinatorial number of solutions to attack forceful manipulation problems across a variety of different domains. So I do want to take a few minutes at the very end to talk about what are the ideas that we're interested in and kind of pursuing now, and things that I see as kind of future/current work, depending on which of these things. Right now, we've seen tool use throughout the talk, but I'd argue that it's like a very simple first step towards using tools. I didn't cover it, but there's been a lot of literature on how we can use tools to extend a robot's kinematic reach. If you've ever seen a paper where a robot's grasping a tool and pulling something, this is an example of that. And extending your kinematic reach is actually one of the 4 canonical tool use tasks as defined in the animal tool use literature. I'm looking in, and this may not surprise by the title of the talk, of how we can look at another one of those tool use applications, which is using tools to amplify mechanical force. And getting into, right now we've been using tools in very standard ways, but you can imagine what if you get into tool creation or tool MacGyvering, where you're using tools in more creative and unexpected ways in order to amplify your mechanical force or leverage it in different settings. Towards that very end, we talked about this notion of robust planning and accounting for uncertainty in our physical parameters, and I'd argue this is good, but this is only really just like a first step. And there are people in my group, I mentioned this at the very beginning, who are looking at how can you deal with uncertainty in future state and uncertainty in your current state. Those are kind of 2 different flavors of uncertainty. And you can think of tackling this uncertainty as kind of loosening that restriction that we have of either needing models that are accurate or needing models at all, right? When we're doing the robust planning, we relax the idea of needing the exact friction coefficient. What I think is neat is that a lot of that work has been dealing with things that you can sense visually, maybe reducing uncertainty in the pose of the object. And for forceful manipulation tasks, because you're interacting with the environment, you really need to act within the world, for example, to get a sense for what is the actual force that you need to exert in order to accomplish this task. And I think this forces you, pun intended, to engage in this loop of interactive perception, estimation based off what happened, and replanning. There's an interesting question of how far back do you need to replan based off how much force you need to exert in order to actually accomplish the task. And the last thing I want to mention, and I'll front, this is the thing that's taking up the most space in my brain right now, is if you are considering forceful manipulation of elastic objects. And here there's a really interesting relationship between force, motion, and deformation. Because if you're dealing with elastic objects, in order to maintain that deformation, it's not stable. You need to maintain exerting that force to maintain the deformation, and so you need to maintain a contact exerting that force. And so if you take kind of an example illustrative task of like a robot inserting a battery, it needs to compress that spring, not just at the beginning, but it needs to maintain the compression of the spring throughout the entire task. And so you need to maintain a contact, and you don't have enough room, so you actually have to use the battery itself to create that contact, but you have to switch over what contacts you are using while always maintaining that you're using something. And so we've been looking at how can you extend our tools from not only task and motion planning, but multimodal motion planning in order to do this search over contacts while still doing your kind of what people consider high-level search, and incorporating this maintenance constraint that we think is very indicative of any time you're dealing with elastic or, to be more general, elastoplastic objects. So that is in progress. I'm happy to talk about it more, but it's still, we're still thinking through it. And with that, that's all I have to say. I want to thank everyone, hybrid or in person, for their time.
All right. There's no written questions, so if you guys have any questions in here. Nick?
Yeah. Can you talk about the experience of if you wanted to use an Allen wrench or a new tool for the robot, the kinds of properties and that process that you would make?
Yeah. So I think for that, we assume, getting back to the assuming models, for what I'm doing right now, a model of those objects and a couple of physical parameters. It's mainly mass, center of mass, and friction coefficient. Again, I have lab mates who are working on relaxing this assumptions. I take the planning, they take the perception. You would then need for that some notion of how are you defining the goal. Is the goal to twist a nut? Which I think in the Allen case would make sense. We've also thought about if you wanted to define goals at a higher level and make the robot do the reasoning over, like maybe you specify the goal as attaching something and the robot has to reason over screwing a nut in. And then for that, you might have to define some level of domain-specific operators. For operating an Allen key, I don't actually think you'd need to, because I think what we have works. And I also want to emphasize that even specifying domain-dependent operators, there's a lot of overlap in that, for checking the forceful kinematic chain or for checking the parameterized controller, all of that could be reused. But off the top of my head, that's what you would need to specify a new domain, at least within the context of this framework. Yeah.
So I had a question about is how fast your robot can move to do these tasks, and is there a reason that it has to move super slowly? Or
I'm scared. That's the fundamental reason. So this robot can move considerably faster than what I'm showing here. You'll notice that all my videos are like times 6x and times 10x. That's because I'm intentionally not running the robot super fast, especially when we get to the cutting. I do care about safety sometimes, Celeste. We do make a quasi-static assumption, and so we're not getting into particularly dynamic actions, but there's really no reason that you couldn't run that joint position controller faster.
Do you think it affects the grasping and the friction when it does move faster, or no?
I think there would hit a point where you're doing dynamic actions and you're breaking the quasi-static assumption, where that would be different. There's a group at CMU who's done like a snatch and grab, and there I think you have to think over different mechanics. That's Ankit's work. I think in general, most robots, when they're operating with objects, are kind of gentle. But it'd be interesting to see, like, if you want a robot to operate very fast, for example, if you're in a factory where time is of the essence, then there might be some things that you have to modify.
We do have a written question is, do the robots ever come up with solutions that were not intended? Something like with the push top, do they ever just calculate what force would be required to break the cap off by pulling it or crushing it?
Our robots are not quite that destructive. So what I would say, in one way, I define this is a set of operators, this is the action space, and kind of any solution that it finds is something that I would not expect because I'm not prescribing that specific solution. There's a trade-off of you are constrained, you will only find solutions that are combinations of those sequence of actions, but you could find any solution that is a combinatorial combination of those actions. I will say you could define the operators a bit more generally. This is something, and there's I think a trade-off here in terms of specification, that you could imagine that I could define an operator that is just exert a wrench in a direction, and that is unstructured and so may be hard to plan with, but could lead to more general solutions like shaving the cap off is what they said. But it's not something that's currently captured here. So yes, it does surprise me, but in a structured way.
Any further questions?
Maybe I missed the early part of the presentations. I have a question in the control input of the current robot. So the control inputs are the torque of each joint and the force in grasping?
Mm-hmm.
Those are correct?
Those are the things that we... Yeah, well, so we run different controllers. So for the first robot that was bimanual, it was all position controlled. And so we had an estimate for the torque, although we couldn't directly sense that, and we controlled the joint angles and the grasping. Actually, for that robot, we could just grasp. It was a fixed grasping force. For this robot, we can run, within this project, we did various position control, joint position control, Cartesian impedance control. We can control the grasping force. This robot, we have a bunch of different controllers that we didn't use, like, for example, velocity control, joint impedance control, force control, torque control. There's a wide range. But yeah, we assume we have a kinematic model of the robot and a notion of its torque limits. Those are kind of the assumptions that we make about the robot.
One last question.
So in the realm when you're thinking about, you've got good models of the tools of the robot, I wonder if you get more headroom or more things become possible if you could design a tool-changing system or integrate the design of these tools with the robot.
Yeah. So in one way, we don't, so often tool-changing systems in industry are that, like, I swap out the tool. We get away from doing that because the tool is not rigidly attached to the hand, and so it's grasping kind of, it has its choice to pick up different tools. I think that designing the tools could go in two different directions. One is you could actually, factor in design optimization along with motion. Actually, some people in my lab have looked at that in an admittedly simpler setting. I think the other thing that I somewhat hinted to is that right now for a lot of these tools, we're kind of prescribing how you interact with it. If you more generally define, like, this is a flat contact area and you can make contact in any way, then you can imagine, like, the robot using a stick as a tool because it understands that it can make different contacts and exert forces through that. I think that's where you would get closer to tool creation and MacGyvering kind of found objects. There's been a lot of great work at Georgia Tech that's looked into this. Sonia Shinova's group, particularly.
All right. Well, we want to thank Rachel for a wonderful presentation. Thank you, guys.